So this is the second video in the series for active learning, and I'm still very much uh, pursuing the same flow. Flow, so to say, what I was doing earlier with this presentation. So just quickly, I will not recap or anything, but just to set context, I'm just following the same flow. And for now, I'm focusing on lightly. And this is the code. I have run this earlier a couple of times. There are few things which I thought had changed, but it seems to still be the same, and it seems to run. Uh, I will quickly go through the code. There is not much over here. First is just setting up, your environment, checking your torch version, other things. Detectron might not work with certain this thing, but that's okay. Over here, in this particular this thing, we've not used much detector on any which ways. And where is this on their official? It is tutorial SimSiam ISA. ISA as in uh, they are wanting to use some. Yeah, they're wanting to use some Sentinel data set, which is basically Sentinel, the satellite images. Uh, but I'm lazy. I don't really want to do this. Earlier, also, I've done it with some other images that I found, that they had recommended on some other, uh, I think, in some issue or something of theirs, which is okay. Doesn't really matter. So, yeah, the concept is what we are actually pursuing right now. Any which ways, I just have one single GPU. Uh, this is not something which is doable in 10-15 epochs. It is just running for 10-15 epochs. Um it is giving sad results right now. Those images I'm using are also not very easy to by any which ways. So before getting into a lot of negatives, let's look at what is happening. So num workers, uh, how many processors or multi-process will be available. So this is one link you need to go through. uh, what will be the batch size for one particular batch? So there's a maximum size. I doubt if I have so many images. Seed is one. Okay, just setting the seed for repeatable, sorry, for uh, making sure that your code gives representable and repeatable results. The epochs is set to 50. I don't think so. We are using 50 somewhere. I think we are cutting it down to 10 or something. I'm not sure. Input size and num features is dimensions of the embeddings. The embeddings to be extracted. We'll get to see all of that here. So there is a very detailed log I've created. So you can see the actual embeddings and tensors. Uh, I will have to spend some time to explain all of this, which I don't know if I want to do right now. Um so this is just the part to the data, the train data and test data, and then there is a image collate function within which they have got whatever transforms are there, and then they say okay fine, we are not doing the transforms over here, which is fine. Then the batch size and all already fixed up there. So let me just run this code, and let's so just to show you, this is um these are the images on which we are trying to do the final k nearest neighbor and the prediction. Uh, this is the code which is running. So give it just a different log file, and that's all. Yeah, and let it run. So let's see, and go to that directory and just, this is the log file, right? So this log file will get populated till the time it is running, and till that happens we can have a look at the earlier log file. This is the earlier log file. So I will get into detail of all of this later, But what we really need to look at over here is this. Mm, okay. So this is just what kind of data set is there and all that. So simple stuff. But what is interesting is this. This is the SimSiam model, and so firstly the backbone. What all layers are there? Sequential layers are there. Backbone of type sequential, right? And this. So I think if I'm not wrong, this is a ResNet backbone. So nothing very interesting here. So same structure. So you'll have a convolution two-dimensional layer. You'll have a batch norm two-dimensional layer. You'll have the kernel size, the stride, the padding. Padding is basically the stride is how many steps you will move in the convolution, and padding is how much you will have around the image. Which you will not basically stride into, or which you will not really convolve into. Uh, so yeah, so all this is okay. Down here you get to see the projection head and prediction head, right? So how are these how are these defined? That is interesting to us. That is over here. So this is the projection head. This is the prediction head. So here you get to understand that with the neural net dot module, which is the PyTorch class, how do you end up defining a network, and then how can you define your own layers, which is your your end layers, which have been defined over here. And if I remember correctly, the last linear layer has been removed. That is what is being done over here somewhere, right? I'll one second. Uh, so at some point here, I think it is in this class only. Yeah, fine. So that resonate children, it is saying my -1 on that particular rest. So remove the classification head. So they've removed the classification head and they've replaced it with the projection head and the prediction head, right? Uh, so this is the basic change in structure, and that is how they've created the SimSiam. Okay. Going back to the log file, if it is done, what happened? No such file or directory. Why? Okay, this has failed because of some path and all that I've given incorrect. I'll fix that later on, not a problem. So what I basically want to do now is I want to show you what was the results of the earlier this thing, right? So now this was the results of the earlier one. So it gives you if you look at this, this is pretty much okay. This came out pretty much okay because you've given it certain images, and it has put those images on this graph. Basically, the distance between those images. So this is of a professor. This is of a lady professor. Again, of a professor with a tie, and some other professors. And all these images have been put separately. As far as distance and everything is concerned, this image is of the same lady, but for whatever reason, okay, this has been so. Also because the model might not be trained very well in very in a small number of epochs, so that's the reason. So we get this example image. Now you would expect it to work probably this way. I don't know. Maybe the example image, which is image 3, will have the nearest neighbor as probably this professor or the student's image, and not any other one, is what I would think. Right? But it has given us this one, and it is inconsistent. If you look at the rest of the this thing, it is very inconsistent. I had excellent results when the images I was using were easy. They had easy objects to define, and probably the embeddings came out pretty much okay. I had excellent results on this, but with these images, it obviously fails miserably. It had not been able to extract the embeddings properly. And this is what I picked up. I picked up from Caltech 101, uh, just as an example. Um, Going back to the code. Uh, so yeah, this is what it is, and I've collated some. I've collated some knowledge base. I'm calling it definitions. So I'll quickly go through this. Uh, so what is the container sequential class that we've defined? So basically, you will end up putting all your layers and stacking them in that container sequential. So it is just very similar to what used to be the Keras code. This is PyTorch, this thing. So categorical classification problem. Okay, classify image inputs, whatever. Multi-layer perceptron. Where do they discuss this? They start off with this paper, right? So this paper is no, sorry, this is FaceNet. Where did that go? This is FaceNet. Where is their? I think this is the one. Yeah. Okay. So on in this paper, they start off with the very simple definitions for the SimSiam and the uh, Siamese networks. So Siamese networks we need to understand if we want to achieve anything with this paper or with this. Uh, so Siamese networks have become a common structure in various recent models for unsupervised visual representation learning. These models maximize the similarity between two augmentations of one image subject to certain conditions for avoiding collapsing solutions. Right. So collapsing solutions. Uh, okay, that I will have to again focus on maybe later on as to what is collapsing solutions and what exactly is collapsing and how to avoid that and all that. So in this paper, we report surprising empirical results that simple Siamese networks can learn meaningful representations even using none of the following: negative sample pairs, large batches. So you don't have many negative sample pairs, still they're giving good results. You don't have large batches, still it is giving good results. Momentum encoders, this again I will have to check. Momentum encoders, I think it's got to do with the momentum value that you are providing to the neural net, right? That's one of the parameters, is what uh, uh, yeah. So maybe they are referring to that. I'm not very sure, but I think that is what they're referring to right now. Okay. So again, this we need to spend more time on this. So everything needs more time to actually understand how it is running. But the code is pretty simple. So the code is pretty simple, and I've gone ahead and I've put it over here. No, this is the old one. Uh, this is again old one. Yeah, this is where I put it. Right. So those run logs are there that within that knowledge base, this one is there. So okay, and I've given links for multi-layer perceptron, how to understand. And again, this is my old own notes from way back in 2017. I've given these links also. And just to quickly go through these links, right? So this is all there. So this has got some old R code, but that doesn't really matter. So what you can focus on is this. So perceptrons are very simple. So it's just it is probably the simplest neural net. And when you say multi-layer perceptron, so this is what it is. So it's we will not call it a deep neural net because the layers were called hidden layers back then, and you maximum had maybe 3 4 layers, and that's how it was defined. And this is from way back in 2017 that I had done this. So again, some of these notes are there, and some R code is also defined, and rest of it is defined here. So you can always have a look at this. There'll be a lot of other examples, this is of Siamese networks, and this also I have mentioned over here. So all of this I have mentioned over here, and this is on GitHub. This file is on GitHub. So this file is here, right? Definitions. So, and I'll keep on updating this. So you'll find a lot of things to read over here and understand the basics before you jump into. And of course, FaceNet has been referred to a couple of times because of the Siamese networks, and yeah. So all of this is here, and running their code is pretty simple, straightforward. So once you run their code, then and you get to see these results. So what I'm trying to do is I'll get better results, and then I'll come back to the code. Then I'll do a code walkthrough only after I get better results. For that, I might have to change parameters over here, or I might have to, you know, change epochs and all. But definitely did not run for 50 epochs. How did this happen? I don't think so. It ran for 50 epochs. Any which ways, even if it did, it is not training properly, because I've trained this same code earlier and got good results. So okay, that is what I want to do. And uh, and yeah, this is where the heads and everything is defined. Again, this code also we need to do a thorough walkthrough, because this is the projection heads defined for almost um, each and every model of theirs. So whether it is Barlow twins or whether it is SimSiam, SimCLR. So if you really want to understand, uh, any of their work, so almost 12 of them are defined, it seems. Yeah, SimCLR, SimSiam. So all of this needs to be gone through in detail. Just running the code is okay. So running the code, that is okay. Yeah, and this structure is very important. So to understand why they have this in this manner, further need to understand. And then, of course, you can just like I've printed very detailed logs. You can print detailed logs to understand what are the tensors which are coming out. The tensor structure is pretty simple usually. Uh, you'll have whatever numbers are here. You will have numbers for embeddings. You will have um, numbers for some kind of classification. There's a lot of detail which will come out over here, like you've seen, and all of this can be gone through and understood. And I will post all of this along with the log files and everything on the GitHub. So yeah, that is what it is for now. Thanks.